Good afternoon, everyone, and thank you for joining us on our call today. My name is Nicole Van Wert-Quincy, and I'll be your moderator this afternoon. Our webinar topic is 4 common pressure calibration pain points, and it's being presented by Jim Shields from Fluke. Jim is a technical specialist and product manager for the process calibration group for the Fluke Corporation. Throughout his career, Jim has been active in the ISA and has actively supported and developed instrument training curriculums. Jim has worked in the field of calibration and metrology for over 40 years. We expect our presentation today to last roughly 30 minutes, and then we'll answer any questions that have been submitted during the presentation. During any time during the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is going to be recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Jim.
Thank you, Nicole. Welcome, everyone. As Nicole mentioned, I'm Jim Shields, our product manager here at Fluke for process calibration tools. And Fluke has been serving this industry for instrumentation and the pressure calibration market for well over 20 years now. In fact, one of our first major partners in this activity was TRANSCAT, who has been doing this quite a bit longer than Fluke. But between Fluke and TRANSCAT, there's a lot of combined experience and tribal knowledge around pressure calibration and testing. Our experience with the instrumentation professionals is that they are a vocal power user of professional test tools, spending years listening to users of tools, what they like, what they didn't like, and where the how they make the work stream easier or harder, where the pain points are the things that as a manufacturer of products that serve the industry, it's where we learn about how to make products different or better. Correlating the feedback from end users and customers and matching that with enabling technology, it's then our job to use technology to address the pain points to find better ways to perform difficult tasks. So the theme today for our topic is pressure calibration pain points, and we've picked on 4 pressure calibration pain points. There certainly are other pain points that we could address and cause some issues with professional pressure calibration users, but the pain points we've selected to discuss today include pressure calibration and leaks, how leaks will affect my pressure calibration and the causes of these leaks, and some tips on how to mitigate the effects. And another item that's a challenge to a lot of instrumentation folks is documenting a pressure calibration. How do you document a calibration when your hands are already full of tools to do the job? See the example in the picture there. There's a calibrator in one hand, a pressure module in the other. Where's the clipboard go? How are you going to write that stuff down? Well, there's some ways to make that easier to perform. And when you're performing a pressure calibration test, it's almost always more than a one-stop pressure test. You're not going to pressure to one test and call it good. The industry standard typically dictates a 5-point up and down test for testing the full linearity and hysteresis of a pressure transmitter or pressure process pressure device, and that takes time and ultimately some tool skills in knowing how to operate your hand pump to hit the pressures and make the test valid. And then lastly, the subtopic is testing pressure switches and achieving repeatability. Because really, without repeatability, which test would you trust? You have to have something you can hang your head on that repeats to know that you've got the actual result for the test. So first we're going to talk about pressure calibration at leaks. Leaking pressure test setups in the field often will lead to failure. The mythical perfect seal is very difficult to achieve. And more often than not, residual leakage is likely to remain. So mitigating and minimizing to reasonable levels is a typical compromise for doing a pressure test. Plus, you want to hold the pressure stable for a period of time to let the output of the device you're testing to settle. Often transmitters will have damping settings that can result in a delay in the output settling for a change on its input. So holding the pressure stable for a period of time is necessary in many instances to get a good test result. And specifying and selecting test hoses and fittings can be confusing. There's all different sizes and shapes. NPT, when to use, PFTE, aka Teflon tape, to seal fittings and when you don't need it, and how to seal and how to mitigate leaks by having appropriate hoses and fittings. There's a lot of good solutions out there, but trying to find the right one can be difficult. And the pressure source, the hand pumps that you use, the other sources of pressure, to achieve the correct result, you need to evaluate and determine which one is best for your application. So classic due diligence is to debug your test setup before you leave the shop. The mission, if you will, is no leaks and the ideal test setup once you get out to the field. So start with quality hoses and connectors. Okay, start with the connectors that you know are going to be reliable and offer repeatable performance. There are hose and connector kits that offer tool-free connectivity. They don't require wrenches or PFTE tape. They have face-fitting O-rings and seals that allow you to hand tighten the fittings into your device that you're testing, and not use any tools or wrenches. So these fittings are available from a variety of different manufacturers, and I think TRANSCAT has 3 or 4 different vendor lines of specialized fittings that make pressure calibration easy. So that's something you may choose to talk to them if you have some problems with your fittings in your test kits. Now, if the installation requires tools, particularly with national pipe thread type fittings, PFTE tape is almost always required. 3 to 4 full wraps of PFTE tape will usually do the job. Don't be cheap, tape's expensive. Make sure you clean off any old tape before wrapping new. And always wrap the tape in the correct direction or it will unravel as you install the fitting. Now, an alternate to PFTE tape is PFTE thread sealant. The thread sealant is a fluid that can be applied to the threads and then tightened, and will offer a good sealing solution as an alternative to tape. So in continuing and looking at your pressure test setup, the debugging, the mission again, of course, no leaks. So once you've identified and your types in your setup, connect it all up on the bench and run through and verify that it does not leak. Connect it up with pressure transmitter or gauge. The pressurized value should hold steady or just count down slowly. 1 count, another count, another count. That's pretty much an example of a good pressure setup, okay? If the pressure does not hold, start troubleshooting. Soapy water using dish soap will bubble easily when rubbed over a leaky fitting. There are commercial versions that are intentionally designed for finding pressure leaks. The most common one I've come across is called Snoop, and it bubbles vigorously when there's a pressure leak that you rub the soap across. So if there's no obvious leaks found in your leaking test, substitution testing may be required to find the culprit that's causing the leak in your test setup. So other methods for mitigating leaks in test setups include nitrogen bottles. A nitrogen bottle in a regulator will tend to hold the pressure steady by pulling pressure from the nitrogen tank and applying it to the test port. And that works great until the tank pressure is depleted. There's only so much capacity in those tanks, and if you're trying to regulate the pressure into a leaky test setup, it's eventually going to fail because the tank, in the source pressure in the tank, will get down below the intended pressure and will no longer regulate. Also, you need to be careful with tanks, as they can be dangerous if dropped. If they drop and a fitting and the regulator breaks off, they can become projectiles. So you do need to be careful when you're working with nitrogen test setups. Another alternate is to use a modern portable pressure calibrator that automatically regulates pressure. There's a number of such tools in the market. One example shown here is the Fluke 729 in the lower right-hand corner of the slide. So that summarizes the leaking pressure pain point. Now let's talk about documenting pressure calibrations. So it's important to know what test tool is a best fit for the application. What does a test require? Figure this out before you leave the shop. Have the right tools. Multifunction calibrators are flexible in that they give technicians more functionality, kind of like a Swiss Army knife calibrator, if you will. They do a little bit of everything. But for pressure, dedicated pressure calibration tools can make pressure testing easier. Many pressure tools have built-in pumps. Some are manual, some are electric, some are automatic. And having more tools built into your test setup is just fewer things you have to carry to the field. And also, it's important to make sure that the pressure measurement tool is accurate enough and matched for the task. If the test tool is being used, kind of a simple rule of thumb, if the test tool is being used at 50% of its specified range, it is probably 1/2 as accurate at that pressure measurement point. So the closer you are to the full scale of the device itself, the more accurate your pressure measurement is going to be. So before you get to the field, if you're documenting on paper, have your methods sheet started before leaving the shop. Have the tag and serial number information, have it recorded and clear what the allowable milliamps deviation is on the device that you're going to be measuring the output of, and make sure all that information is clear and documented on the method sheet. So with your hands full and holding a calibrator, how do you legibly write down the information on the method sheet? Well, many calibrators have hanging strap tools. The example on the lower right, the calibrator is hanging off a pair of magnets. There's Velcro straps, a variety of different ways that you can set the calibrator up to perform the test, but yet allow the technician to have their hands free. So if you're going to manually document the test, consider using one of the hanging tools to allow your hands to be free to record the calibration. And then, of course, there are a variety of different types of documenting calibrators, a variety of manufacturers that can capture results to the field without pen and paper, eliminating the need for technicians to transcribe and write that information down. So more about modern documenting calibrators. They can capture your test results in the field, and one of the beauties of them capturing the results is they do eliminate transcription errors. In the example shown for a calibration test, you can see that in the upper left-hand corner of the screen, you can see the first test, you can see the applied pressure, the measured milliamps value, and the error percent of the deviation for the milliamps. And note that that's in red, indicating that the allowable milliamp deviation for this test is exceeded. So as the test is performed, you get the as found documented test result. And indeed, you have the actual test point, the pressure that's applied for the test, the milliamp signal, and the error of the measured milliamp signal compared to ideal. In this case, the test is flagged as failed, indicating that the milliamps values that were measured were out of the allowable test tolerance. So once the as found documentation is taken, now and again, as found documentation is required by many regulations. Don't perform adjustments before taking that as found data, because that's the as performing condition of that transmitter at that location in the plant. If it's regulatory critical or quality critical, there may be some rework or recourse associated with that device being out of its operating specifications. And again, that's pretty much as documented in the process document for the particular device in the plant. But once the as found data is taken, then adjustment can be performed and adjusted to within tolerance, either via manual adjustment, which is less and less the case these days, or using a tool with heart communication built in to trim the milliamps or trim the pressure zero, or trim to the applied pressure values for zero and span. Once the adjustment is completed, then the test is repeated as left, and pressures are applied and the milliamps are measured and errors are recorded. And if the errors are within the allowable test tolerance, then the errors shown on the display of the documenting calibrator show green in this instance, indicating that they're well within the allowable test tolerance. And then the as left documented test shows pass, as all the milliamp values are well within the allowable milliamp limits, and the errors accordingly. So the as left is proof of the condition of the device when it was put back in service, and proves that the adjustment was successful, or if not successful, it'll prove that as well. And once that as left test information is taken, a tag is recorded of the device, its serial number, and user ID is entered to record the person actually doing the work. Also recorded in a documented record for a documented calibrator are the date and the time, as well as the serial number of the calibrator, and in some instances, if there's external pressure modules being used as a portion of the test, the serial number of the external standards as well. So most modern documenting calibrators have built-in templates and have the ability to receive a calibration routine, or if you will, maybe you might even just think of it as the method sheet for the tag being sent down electronically to the calibrator. The templates define the pressures to apply to a device and its measured output parameters, typically 4 to 20 milliamps, or in some cases the output of the transmitter could be 1 to 5 volts. They define the test tolerance, the number of points, the settling time, transfer function. As you can see in this example, top example for the documenting calibrator, there's a variety of different types of tests that could be performed, and these canned tasks can be then customized and then saved as a customized test for later recall in the event that the default templates don't meet the requirement for a particular device or tag that's being tested. There's also, in most modern calibrators, there's going to be a leak test. The leak test will verify your test setup to see if you've got leaks in it. Okay, so if you think you might have a flaky leaking test setup, many of the modern calibrators, the automated regulating ones, will have a test built in to verify that your test setup is functional. And again, the functionality with this varies from manufacturer to manufacturer. So one other function that happens to be built into, in this case, the Fluke calibrators, is wireless communication. We have a communication protocol we refer to as Fluke Connect that enables communication to remote devices from the calibrator. An example, in the example picture, the calibrator is generating the pressure into a device, and the pressure that's actually being generated by the device is being transmitted to the smartphone. This enables time series measurements to be recorded and logged. In the instance that you have a loop that may be misperforming and you want to record its deviations in pressure over time, you can record that pressure, those pressure measurements remotely to the smartphone. Most documenting calibrators can also log to internal memory for recall and review, but again, the remote logging can be a good tool for capturing intermittent process anomalies. So one of the benefits of using a documenting calibrator, one of the obvious reasons is no writing down of the measurements, eliminates transcription errors, and eliminates the errors from manually entering calibration data into a PC. The poor guy that's out in the field trying to write down legible information on a clipboard then brings the information back into the shop and either has to type the data in that he's written down or pass it on to someone else to enter into a computer. The probability of transcription errors or interpretation errors becomes great the more people that are handling the data. If you pair a documenting calibrator with calibration management software, that enables data analysis and better management of the calibration instrumentation workload. Also, with data analysis, it enables calibration interval adjustments. In the event that you have bad actors, you can shorten the intervals for devices that have repeat failures or are marginal. You can shorten the intervals so the deviation at the end of the calibration cycle is less. Or for devices that are repeatedly less than 50 or 20% of their specification, you can lengthen the intervals and basically give the particular device or tag less calibration effort to maintain its performance within the expected accuracy. Using calibration management software and documenting calibrators optimizes the use of skilled technicians, and one thing that's really big is it enables route-based maintenance schemes. A route-based maintenance scheme enables multiple devices, multiple tag numbers to be loaded into a calibrator and enables the technician to go out and perform the calibrations as opposed to performing one calibration, returning back to the shop, getting the information for the next calibration, and then going back out to perform the calibration. In the instance of using documented calibrators and upload-download with calibration management software, multiple calibrations can be performed in one trip, which really improves the efficiency of the technicians doing the work. So the next pain point to discuss is generating accurate multi-point test pressures. The industry standard often calls for a 5-point ascending and descending test strategy. Ascending, as you can see in the screen example on the right, the test ascends from 0 to 50 to 100% and then descends to 50 and 0%. That's an example of a 3-point up and down test. The industry standard is actually more points than that, a 5-point up and down, applying 0, 25, 50, 75, and then 100% of the input pressure span, and then decreasing to 75, 50, 25, and 0%. For this test strategy on a transmitter with a range, for example, of 0 to 200 psi, you would start the test at 0 psi, apply 50, and then 100 psi, then 150, and 200 psi, and then begin descending down to 150, 150, and 0 psi. So there's quite a few pressure test points to hit. The ascending test portion verifies the endpoints, of course the 0 in span, 0 and 100%, and linearity of the transmitter. When you go into the descending test, you are verifying hysteresis and zero shift. As you decrease, the difference between the measured values, say at 75, 50, and 25% compared to the values measured and increasing, that difference in the measured values is referred to often as the hysteresis error of a pressure transmitter. So generating values and not overshooting the target pressure is ideal for the best result. You don't want to grossly overshoot and induce hysteresis when you're looking to verify a device's linearity in an ascending test. So a minor overshoot within the fine range adjust of a vernier is is typically okay, but significant overshoot can skew the test results, and gross overshoot could potentially damage the transmitter that's being tested or the test tool that you're generating the pressure into. Now, there are ways to mitigate that. There are a variety of pressure relief valves. I've seen some plants put on devices that they continually have issues with being overpressured or blown up for whatever reason, and they will protect them with a relief valve. But on the downside is pressure relief valves, the pressure with which they protect the device needs to be adjusted correctly, and further, when relief valves are misadjusted, they can leak. It just adds another device in the loop with the possibility of leakage. So to make pressure generation easier, start with a debugged proving test setup. Now, high confidence testing is just about impossible if you're trying to fight a continuous leak. And hand pump selection is critical in ensuring that the hand pump matches the test pressure range that you're performing. Different hand pumps have different pressure ratings and have different linearity and resolution in their vernier. So pick the pump that's right for the test. And before you perform the test, center the pump vernier before starting the test. Invariably, if you don't center the pump before starting the test, Murphy's Law says that if you need to increase or turn it one direction and it's on the stop, that's going to be the direction you're going to want to turn it. And remember the position of the pump vernier from one test point to another. There's a little bit of tribal knowledge in working with test pumps that if you remember where it's left in its vernier phase, you can overcome its position by virtue of the way that you pump to your target pressure with the pump. Another method, not always achievable, is to remove the transmitter from the process in cases where the devices are being maintained in an outage. Testing on the bench is a much more controlled environment. There's a variety of bench test calibrators that work off of nitrogen bottles that allow you to do automated tests. So there's a large variety of different types of tools that can make bench pressure calibration easy. Or you can use a new generation portable automatic pressure calibrator like the legacy Transmission 190s. The TRANSCAT was selling the Transmission products 190 for many years. It was selected and used and loved by a lot of the technicians, but it's now gone away, and there's a variety of new pressure calibrators out there on the market, such as the 729 automatic pressure calibrator showed below it. So talking about testing pressure switches, it's really all about achieving repeatability. Without test repeatability, again, which result would you trust? Flip of the coin? How many tests do you need to make before you can get this repeatability? So pressure switch testing typically requires a good deal of tribal knowledge, good knowledge of the hand test pump that's being used for the test, the ability to get the test pressure within the range of the fine adjust vernier is critical. When the applied pressure is close to a switch state, the pressure rate must be slowed down to get repeatability. And the reason for that is pressure calibrators typically have a measurement reading rate, and if it's trying to trip at a particular pressure when it senses a contact state change, the slower that pressure is moving, the higher the probability it's going to accurately catch the pressure at which a switch opens and closes. So slow down the change rate of the hand pump and have a tool that has a fairly high-speed pressure measurement rate, and then you can get best repeatability for your tests. Also, running the test multiple times and verifying that the test results do repeat. You can't tell if you have repeatability unless you've run the test twice, or if you have a tool that's going to going to guarantee that you are getting repeatability and reliable results on your test. So pressure switches usually have 3 connections, a black wire for common, a normally open and a normally closed connection. A number of the switches that I've worked with, there's a wiring, red's the normally open connection wire and the green wire is normally closed. And one or multiple contact states of a switch might be used for pressure sensing. So to run the test, connect one test lead to common, and the other test lead to either the green or the red wire, depending on which state of the switch needs to be tested. And then make your pneumatic connections from the output of the pump or calibrator to the input of the switch. So looking at the terminology of a switch, the reset state is the relaxed state of the switch. For normally closed contacts, the reset state is shorted. For normally open contacts, the reset state is open for dry contacts. The pressure applied to the switch for the reset state typically follows the setting for the set state by the amount of the deadband typically. So there are a number of premium pressure switches that do have both an adjustable set point as well as an adjustable deadband. The set state is a state of the switch when it changes responding to an applied pressure. So where the contacts open or close with an applied changing pressure. So the diagram depicts 2 normally open switches that set when the pressure gets either too high or too low. For a given set point, the difference in pressure between where the switch opens and closes, where it sets and resets, is referred to as the deadband of the switch. The deadband is the area that the process pressure will cycle within acceptable limits before changing state, triggering a control device or other action as triggered by the opening and closing of the switch contacts. This is an example of a test being recorded with a manual calibrator. The first portion of the test is to explore and find where the set point is reached, where the switch either sets, in this case shorts, and the pressure applied for it to do so. And then slowly release the pressure and note where the switch resets. After the first pass, then you can creep up to the set point pressure and then slowly increase the pressure using the fine adjust vernier of the calibration tool or pump. If you approach the target pressure nice and slowly, you're going to get your best result and best find the pressure that the switch is setting or resetting and capture that and get best repeatability. 2 tests that correlate are required for a repeatable test conclusion. It requires tests beginning with the exploration, as I mentioned, with slowly changing pressure and then repeating, creeping up on the set and the reset point, and then recording and making sure that the values do indeed repeat. The example tests shown were captured with a 718 manual pressure calibrator. It's a pressure calibrator with a built-in manual pump. And this normally closed switch set by opening its contacts at 184.1 inches of water, and it reset at 290.5 inches of water when the switch is closed, when the switch contacts closed again. And then the calibrator would calculate the deadband as being the difference between the 2 pressures at 106.4 inches of water. So you can get good results with a manual calibrator, but it does require some skills in getting the applied pressure within the range of the fine adjust vernier. Automatic pressure calibrators with a special purpose test procedure can automatically perform this test. You define the expected pressure for the set point and the deadband, define the maximum pressure that the calibrator will pump to. That basically helps minimize the chance that you're going to overpressure the device. and describe the switch type. Is it normally open or is it normally closed? And the switch shown there is an example of a test being performed on a pressure switch. You can see the set point, its allowable tolerance, the minimum and maximum sizes of its deadband, the maximum pressure that the calibrator will pump to test the switch, and its switch type. So once configured and run, the test runs and displays results automatically on a pressure switch. It explores and retests and achieves repeatability. If you take a look at the first screen in the top, the automatic test is started. The switch contacts are identified as being normally open. And as the pressure increases and the contacts close, the set point is found. And once the set point is found, the pressure is released until the reset pressure point is found and the contacts open again. And then once completed, the test summary is presented and the recorded this calibration result for the switch is recorded in the documenting calibrator's memory. You can see where the switch set, it reset, the size of the deadband, the deviation from the ideal set point, the set point error, and the deadband error, which in this case there is none because the deadband was found to be within the minimum and maximum size defined in the pressure setup test. So talking about the pain points and mitigation, pressure leaks, debug your test setup, use a nitrogen bottle and a regulator, or use an automatic regulating pressure calibrator. Some shortcuts to mitigate pressure leaks. For documenting pressure calibrations, automatic documenting pressure calibrators make documenting easy and paperless. Also using hanging tools to free up your hands for recording your calibration data. Generating accurate pressures for a multi-point transmitter test, a debug test setup, and or an automatic pressure calibrator makes this easier. Testing switches and achieving repeatability, skill and experience with a hand pump, or leverage the test routines built into an automatic pressure calibrator make this difficult task easier and easier to achieve repeatability. I want to offer thanks to our host, TRANSCAT, for hosting the webinar today. If you have pressure testing pain points, they have experts to the field to suggest hose kits, a variety of pumps, industry best selection of pressure calibrators. They also offer the premium automatic pressure calibrators like the new Fluke 729 that help eliminate pressure testing pain points. And with that, questions or comments, I'll throw it back to Nicole.
Thank you. Thanks, Jim. So that concludes our presentation portion of the webinar, and now we're going to open it up to the question and answer portion of the webinar. I do see a couple that came in. Let me see, the first one, it says, I guess that using a documenting calibrator in an FDA-regulated environment will require that you validate the instrument software. If that's the case, can TRANSCAT or Fluke provide any documentation that can support such validation?
We, at Fluke, our DPC Track 2 software platform is not an FDA approved application. However, we do partner with a company called Prime Technologies, and their ProCal is an extended subset of our entry-level DPC Track 2 software, and they do have scripts and professionals that can help with the FDA validation in the event that that's a requirement for your regulated working environment. So that's something that if I believe that if your question comes into TRANSCAT, I can certainly direct it to our software partners in the event that they wanted to get some more information on that. But yes, there are scripts available that will help with the validation process.
Okay, thank you. And just as a reminder to anyone that's on the call, if you'd like to ask a question, you can send it through the question box, which is in the right side of your webinar controls. So let me see. Let me go to the next one. How do you slow down the pressure change rate when testing switches?
Got it. Well, I mean, the real trick is pumping up as close to the pressure as possible. And once you get as close as you can get to a trip point without the switch opening or closing, have your fine adjust vernier available at your fingertips and very slowly dial it up to the point with which it trips. The slower you're moving your pressure, the slower the change rate is going to be, and the higher the probability you're going to get your best trip when you actually do get the switch to open or close at the pressure point and record the best value for repeatability.
Okay. Does Fluke offer a documenting pressure calibrator that is also intrinsically safe?
We do not have an automatic pressure calibrator that's intrinsically safe. We do have a version of the 718 that was briefly pictured in the presentation that is intrinsically safe. And we have 3 different pressure ranges, I think a 30, a 100, and a 300 PSI version, but you are relegated to a manual pump operation in the intrinsically safe version.
Okay. And of course you can get that through TRANSCAT if you want that.
Yes.
Just thought I'd clarify that one.
Yep.
How do you hold pressure stable with a manual pump?
That's a challenge. And if the leak in your test setup is too large, it's almost impossible to do. However, if you have good range in your fine adjust vernier of your hand pump, and you pressure up to just above your pressure calibration target pressure point, and slowly hold the vernier of the pump and turn it, you can often compensate and hold the pressure stable applied to the AUT. It's suboptimal compared to a good debug test setup, but I've seen technicians do it and get the test done. So that's the method I've seen folks use. It's obviously easier to have a regulator and a nitrogen on a nitrogen bottle or an automatic regulating pressure calibrator to compensate for those leaks. But if you don't, being clever with the fine adjust vernier on your hand pump will often give you the same result.
Okay. A gentleman asked if the 718 down, he says, will the 718 download to ProCal?
The 718 is a manual test tool. It will record the trip of switches real time on its display, but it does not document and offer upload download with calibration management software.
Okay. Let's see. Someone duplicated a question. We use a Fluke 754 and several 750 series pressure modules. I found that sometimes the 1 and the 5 PSI modules are quite difficult to zero. I press the 0 button and the module will give negative 0.3 inches of water reading. Sometimes it takes 8 or 10 attempts to get the module to remain at 0. I'm not sure what that, does that sound like something you've heard?
Yeah, I wonder what can happen is if a pressure module or a pressure transmitter sees over pressure, the actual physical measurement area inside gets slightly distorted, and you get difficult with zero shift repeatability. You might want service to take a look at that unit. Normally 0 is fairly repetitive unless the device has seen potential overpressure. So you may want to check and see if that's a service issue. Okay,
a couple more. The range for the 729, if it is a standard 300 PSI, then do you have another for higher pressure ranges like up to 3,000 PSI?
To go up to 3,000 PSI, we offer pressure modules as accessories in high pressure pumps. In the case of, there's a variety of different pumps that you can use that can get you to higher pressures. There's a hydraulic hand pump that will easily get you up to 10,000 PSI. And there's also a new pneumatic test pump that will go up to, I believe, will go up to 3,000 PSI. So there are options to get you there, but it does require external accessories.
Yep. Okay. Do you find that dial pressure gauges often perform poorly in terms of hysteresis?
Dial pressure gauges being a mechanical beast, if they have seen or been hammered with overpressure or rough service conditions, they indeed can have both linearity and hysteresis problems. So it's going to be directly related to the method of service that they're installed in. I know that in not in dial gates necessarily, but I know with some of the older Rosemount 1151 transmitters, for example, by function of getting hammered, they exhibited significant hysteresis errors on declining pressure tests. The more modern Rosemount 3051s are far superior to that in that regard and are much more tolerant. But hysteresis, depending on the roughness of service, hysteresis is most likely going to be a problem in rough service applications.
Okay. Those are some great questions, and I think we'll wrap it up right now. That concludes our time for today. If you have further questions or would like to find out more about TRANSCAT's products and service offerings, you can contact us at the 800 number on the final screen, which is 800-800-5001, or on the web at transcat.com. Or you can email me directly after the webinar at nvanwert@transcat.com. We appreciate that you took your time and part of your afternoon and joined us today. And we hope you got something out of the presentation and that you continue to join us for future TRANSCAT e-learning webinars. Thanks so much, Jim.
Thank you, Nicole. Thank you, everybody, for joining us.
Take care.
Thanks.